Hello. So, welcome back. Here's the second in the series of video lectures. I'm sorry I am not able to be there today, Wednesday. So I wanted to just sort of remind you where we were. In section 5.1, we introduced the concept of a eigenvector and eigenvalue in order to resolve linear transformations. And just to remind you of the definition, whether we're dealing with a linear transformation from Rn to Rn, or a matrix A, a square matrix, we say a non-zero vector is an eigenvector of T, or an eigenvector of the matrix A if when I plug V into T, or I multiply V by A, I just get a scalar multiple. So I think of this as a blob. So A times V is a blob times V, okay? And that's an eigenvector, and again, it's important that it's non-zero, okay? In this case, we call lambda the eigenvalue associated to V, and remember, that's sort of just a scaling factor in the direction of V, okay? And eigenvectors, again, have to be non-zero, and what we are really looking for is a basis consisting of eigenvectors to resolve linear transformation. And we prove theorem 2 in this direction because we want a basis, which is useful in that, that just reviewing, if I have eigenvectors, let's say I've got k, 5, 10, whatever, and I've got distinct ones, so in other words, none of the eigenvalues are equal, or the stretching factors or compressing factors, then I'm guaranteed to have a linearly independent set. And this is the start, one of the things we need for a basis, because the basis needs to be linearly independent and generate. But this gives us linear independence for free if we've got different eigenvalues. So we had gone through the proof of this on Monday. And so this led us to our strategy in terms of finding eigenvalues and defining the characteristic polynomial. Again, our strategy is to let t be a variable and look at determinant of a minus ti. That's gonna, whenever that's not invertible, then we have an eigenvalue, okay? And then to find the corresponding eigenvectors, we take the corresponding null space here. And once we have those eigenvectors, then we've got the whole situation. Okay. This led us to defining the characteristic polynomial. Okay, and that's just going to be this expression determinant of a minus t times the identity. We go ahead and take that determinant. It's a polynomial of degree n, and that way we've got a polynomial. That polynomial will have at most n roots, and these will give us the eigenvalues. And once we have the eigenvalues, we can find the eigenvectors. We did talk about this special case when we have upper triangular matrices, because determinants are very easy then. And so here's an example where I have an upper triangular matrix. I have diagonal entries 3, 5, 7. I subtract off t there, and I end up with a product of 3 terms, and I get eigenvalues 3, 5, and 7. So at least for an upper triangular or even a lower triangular matrix, the eigenvalues correspond to the diagonal entries. Again, there's this caution: row reductions change eigenvalues, and the characteristic polynomial, so do not row reduce before introducing the variable t. And so I want to switch here to this example. Just to go through, we went over this example on Monday, but just to review it, sort of how does this process work? And so first we would find, we'd subtract t off of each diagonal entry, take the determinant. We looked at how to do that on the calculator. Go ahead and factor it. I have these 3 linear factors. So my 3 eigenvalues are going to be lambda equals 0, lambda equals 3, and lambda equals -2. Okay, and so we get these 3 eigenvalues. Mhm. Now, what we want to do is find the corresponding eigenvectors or the corresponding eigenspaces, right? And so what we want to do is we want to solve these corresponding homogeneous equations. And again, since lambda 1 equals 0, I subtract the 0 off of all the diagonal entries, set it equal to 0, solve the corresponding homogeneous system. We get a reduced row echelon form. We solve the homogeneous system. Again, we introduce x3 as a parameter t, and I get a negative t when I move it over here, and I get a negative 2t, so I get this negative 2, negative 1, 1 as the basis of our eigenspace. And again, all multiples of this vector are is the whole eigenspace, the span of that single vector. Right? Now we take the next eigenvalue, right? Let's take negative 2. Since we're subtracting a negative 2, that time becomes a plus 2. And I go ahead and put those in all the diagonal entries. I take its reduced row echelon form. I solve. Again, x equals x3 becomes the free variable. So that becomes 1/2. Yeah, I get t for x3, negative 1/2 by bringing it over here, negative 1/2, bringing it over here. I multiply through by 2 to clear the denominator, and I get this negative 1, negative 1, 2. Right? To get the third eigenspace, again, we take the eigenvalue 3, subtract it off from all the diagonal entries. We solve it. We do the same process, solving with a free variable t, and get the basis for our eigenspaces as 2, 1, 2. Right? Again, t, it would be t, 1/2 t, t, and then I just clear the denominator, multiply through by 2. Right? And so this becomes a, we have 3 eigenvectors. Each one has a different eigenvalue. So by our theorem, theorem 2, this set is linearly independent. By the invertible matrix theorem, its set is also a basis, right? And so again, remember the invertible matrix theorem, when we did that, we didn't have bases. It just says that any linearly independent set of 3 vectors in R3 also is also generates, and so it's a basis. All right. Our second example, what we wanted to do is what happens if you don't have distinct eigenvalues or 2 eigenvectors with the same eigenvalue. And so we wanted to explore that a little bit. And so again, we did this one here. We get the characteristic polynomial. If I subtract t off of each diagonal entry and take the determinant, I get this cubic polynomial, which can be factored as t plus 2 squared, t minus 3 squared. And again, you can do that on the calculator. TI-89 will do that for you. Right? So we go through the same process. We take a look at the eigenvalue 3. We take a look at the eigenvalue negative 2. And we go ahead and take those null spaces, right, solve the corresponding homogeneous systems, and get eigenvectors. And so for lambda equals 3, we subtract 3 off of each diagonal entry. We end up with this matrix. We go ahead and solve it. And now again, x3 is a free variable. So I can bring things over to the other side, and I get 1, 1, 1, right? T, T, T is what's, and so I just take the coefficients 1, 1, 1 as my basis for the eigenspace. So let's take a look at what happens when lambda is equal to negative 2. All right, when lambda equals negative 2, we plug that in. So we subtract negative 2 or add 2 to each diagonal entry. We get this matrix. Notice that all 3 rows are the same, so it makes sense. When I row reduce it, I just get the top row. In this case, this is the only pivot right here. So I have 2 free variables. X2 is free, X3 is free. And so what I can do is I can think of this as, I can think of X3 as T, X2 as S. I go ahead and solve it. X1 is going to be S minus T, so I can take the coefficients of S in one vector, the coefficients of T in the other. And this is a basis for this eigenspace. So this eigenspace has right? Because of the way we solve for null spaces, we naturally get a basis for the null space. And so what I've got is I've actually got a two-dimensional eigenspace here. Well, that corresponds back to right, the fact that this has this factor appears twice in the characteristic polynomial, that this is a possibility. And so so I've got two vectors there has a basis. Now theorem 2 doesn't apply here, but I can check that this set is linearly independent here. So it's going to be a basis of R3. All right, I can put it into a matrix, show that that's going to be invertible. This one has eigenvalue 1. These two both have eigenvalue -2. And so I still get a basis of R3, even though these both are associated with the eigenvalue -2. All right. Now I wanted to take a look at this other example. So examples 2 and 3 are going to be important. And I mentioned this example at the end of class on Monday. So let's go ahead and take a look at this. When I find its characteristic polynomial, I get, again, this t plus 2 factor squared. In fact, this is the exact same characteristic polynomial as in example 2. All right. Let's go ahead and solve the eigenspaces, because the eigenspaces are going to, it's a different matrix, so the eigenspaces are going to be different, most likely. We go ahead and solve. We subtract 3. We go ahead and solve. Take its reduced row echelon form. We get 1, 1, 1. So this is actually the exact same eigenspace as an example 2, right? For lambda 1 equals 3. The thing that happens is when I use lambda equals -2, I plug that in. Notice these are not all the same row anymore. And if I row reduce it, I get the reduced row echelon form to look like this. And there's only one free variable. And so I can make that my x3 being t, bring things over. I've got a -1 and -2. And so -2, -1, 1 is the basis of this eigenspace. It's the only basis element. But this is a little strange, different, in that it's a little strange, maybe not what we expected, in that here, again, this factor appears twice, but the corresponding eigenspace only has dimension 1. All right, so we do not have enough linearly independent eigenvectors to form a basis for R3. We've got one for lambda equals 3, another one for lambda equals -2. And those are the only two eigenvalues, and we only have two linearly independent vectors. Okay. So how do we know we're not missing any eigenvectors? Again, because there are only two eigenvalues, and these are the only ones that work. So to summarize, in example 1, we got 3 distinct eigenvalues, so we're able to use theorem 2 to get a basis of eigenvectors. In example 2, even though we had only 2 eigenvalues, so we can't use theorem 2, we can still find a basis of R3 consisting of 3 elements. Right? In this sense, we double counted the eigenvalue lambda at 2 equals -2, right? And so we talk about that eigenvalue having multiplicity 2, right? To say that t plus 2 factor happens twice, all right? And the corresponding eigenspace has dimension 2, right? And in example 3, though, we show something else that can happen. We have the exact same characteristic polynomial as in example 2, but in example 2, we had 3 linearly independent eigenvectors, and in example 3, we could only find 2 such vectors. Even though we had in example 3, is because of the exact same characteristic polynomial, lambda 2 equals -2 is an eigenvalue with multiplicity 2, but the eigenspace only had dimension 1, because there's only one basis element there. And so we want to use this term multiplicity, and we say let A be an n by n matrix with characteristic polynomial. Let's just give it a name, P of t, right? Where T is a variable, it's just a polynomial in t. If lambda is an eigenvalue of A, then the largest positive integer k is such that t minus lambda to the k is a factor of pt is called the multiplicity of lambda. So it's just how many times does t minus lambda occur in the factorization of the characteristic polynomial. That's all it is. All right. So for example, if I happen to have a characteristic polynomial, t minus 2, t plus 3 to the fourth, I'm sorry, t plus 4 to the third, t minus 1 squared. We would also say that A has eigenvalues, right? The eigenvalue corresponding to this factor is 2. But the exponent here, again, with exponents, if it's 1, we don't tend to write that exponent. And so that has multiplicity 1, right? Lambda equals -4 is the root of this factor. And the exponent here is 3. So it's lambda 2 equals -4 with multiplicity 3. And finally, lambda 1 with multiplicity 2, again, because that's the exponent here. Okay. Note that we can tell that A would have to be a 6 by 6 matrix. Well, why? Remember what we said about the degree of the characteristic polynomial. The degree of the characteristic polynomial matches the size of the matrix. So since this has degree 6, right, 1 plus 3 plus 2, A would have to be a 6 by 6 matrix. Right? So here's the theorem that we need that helps us, at least in terms of analyzing this. If lambda is an eigenvalue of a matrix A, then the dimension of the eigenspace of A corresponding to lambda is less than or equal to the multiplicity of lambda, but greater than or equal to 1. It's got to be at least 1. So let's say if I look at this example here with lambda 2 equals -4, corresponding eigenspace could have dimension 1, 2, or 3, but it can't go above 3. It could be 2 and it could be 1. All right, so we can construct examples of that where it only has dimension 1 or dimension 2. Okay. Right, but this is good to know. I mean, we're not really going to prove this theorem, but it's beyond the scope of the course. But at this point, we're just, it's useful to know. We're going to use that theorem. All right. Now, part of what we want to do is we want to resolve linear transformations by changing bases. Excuse me. And so a useful concept here is this idea of similar matrices. And we will see sort of how similar matrices compare. Okay. And what do we mean by similar matrix? We say that two matrices of the same size, n by n, are similar if there exists an invertible matrix P such that A equals P, B, P inverse. Now note that that may seem like a strange construction, but we find out that this is what's happening when we, in some sense, change coordinates as we end up doing this type of operation. And so we want to talk about how we compare similar matrices. Okay. How do eigenvalues and eigenvectors of similar matrices compare? Right? If two matrices A and B are similar, right? By definition, there exists an invertible matrix. I guess I wrote it this way: B is equal to P inverse AP. Notice that's the same thing because I can multiply both sides of this by P inverse and then on the left, and then multiply by P on the right. Again, matrix multiplication is not commutative, so I have to write it as P inverse AP. So I get this equation from this one. All right. But what happens? To get the eigenvalues, I need to take the determinant of B minus T times the identity. Well, all right, so B is equal to this P inverse AP. All right, how do I compute that? Well, I want to get P inverse and P in here somehow. The nice thing about the identity is I can view this as P inverse AP minus P inverse T times the identity times P. The identity commutes with all matrices, so I can move this on the outside. The P and the P inverse cancel. This is one case where I know I can reorder the matrices. So this is really the same thing as multiplying and dividing by the same number. I'm just putting this in so that it will match this form here. The advantage of doing that is now I can factor out P inverse on the left, P on the right. The thing I know about matrices and determinants is now I can use theorem 6 of chapter 3 and go ahead and write it this way. Okay. Well, here's a characteristic polynomial of A. P and P inverse, those determinants by theorem 6a, this is just going to be 1 over P, 1 over the determinant of P, and this is going to be the determinant of P. All right. And these are numbers, so these commute. I can move this over to that side and cancel with the 1 over determinant of P, and I get the determinant of A minus T times the identity. What did I start? I started with determinant B minus T times the identity. These two determinants are equal, right? They're equal. So what does that mean in terms of characteristic polynomial? When they're similar, they have the exact same characteristic polynomial. So what does that mean? That means that they have the same eigenvalues with the same multiplicities. Okay. All right. So we've proven the following theorem, theorem 4. If two n by n matrices are similar, then they have the same characteristic polynomial and hence the same eigenvalues with the same multiplicities. I will say the converse of this theorem is not true, is that I can have two n by n matrices with the same eigenvalues, with the exact same characteristic polynomial that are not similar. So this goes one way, but not the other. Okay. Right, the two matrices, A in example 2 and B in example 3, are not going to be similar. All right. We will show, and that's part of the homework problem that I'm assigning for Monday, is that if two matrices are similar, then the dimensions of the corresponding eigenspaces have to be the same. And that's not true in those two examples that we saw earlier. And so that's how we know these are not similar. All right. Right. So if two matrices are similar, the corresponding eigenspaces do not need to be the same, but we can prove that the corresponding eigenspaces have the same dimension. And remember, in example 2, the eigenspace corresponding to lambda equals -2 had a dimension of 2. In example 3, the eigenspace corresponding to lambda equals -2 had dimension 1. So different dimensions, they're not similar. All right. And so one of our goals is really to get to diagonalizable matrices. And so let's say a matrix A is called diagonalizable if A is equal to P, D, P inverse for some diagonal matrix D and some invertible matrix P. Okay. So D has to be diagonal. In other words, the only non-zero entries are along the diagonal, everything else is 0. And I've got this invertible matrix, P. All right. That's the same thing as saying if I can find an invertible matrix to conjugate by and get a diagonal matrix. Okay. Again, that's a matter of just multiplying by P inverse on the left and then P on the right, and I get this equation here. All right. So we can say this definition a little bit more concisely by saying A is diagonalizable if and only if A is similar to a diagonal matrix. It's the same thing. And here's the big theorem. Okay, this is an important theorem, the diagonalization theorem. It has a name, so we want to remember this. An n by n matrix is diagonalizable if and only if there is a basis for Rn consisting of eigenvectors for A. Okay, that's the only time it's diagonalizable. Furthermore, this theorem tells you how to diagonalize a matrix, what matrix is similar to, and how to get the invertible matrix P. So A is equal to P d P inverse if and only if the columns of P form a basis of Rn consisting of eigenvectors of A, and the diagonal matrix entries of the diagonal matrix are the eigenvalues of the corresponding to the respective columns of P. So that work that we did in the previous examples, finding basis of eigenvectors, we can use in terms of this diagonalization. And really what we're doing is we're changing coordinates to create that diagonal matrix. We'll get into that and see how that actually works as a coordinate change a little bit later. But let's take a look at this theorem and see how this works. Okay. And it's just the proof of this. I mean, the theorem sounds complicated, but it also gives you a procedure. But this is one of those proofs where they give you the answer and you just check that it works. Okay. We don't need to solve for it. We just show that this actually works. And so let's go ahead and prove it. A is diagonal. Assume A is diagonalizable. So that means A is equal to P d P inverse for some invertible matrix P and some diagonal matrix D. Okay. Since P is invertible, the columns of P form a basis of Rn by the invertible matrix theorem. Okay. And so let's go ahead and let Pi be the ith column of P. So P1 is the first column of P, P2 is the second column of P, P3 is on and on. And what does that mean? That means that P inverse of Pi is equal to this ith column of the identity, right? This ith standard matrix, ith standard vector. All right. And this is not hard because, I mean, if you want to multiply both sides by P, the ith column of P is just P times the ith column of the identity. So when I take A times P, I put in this P d P inverse. I substitute in this for the P inverse Pi. That becomes the standard vector, the I standard vector. D is a diagonal matrix, so what does that do to the I standard vector? It just multiplies it by a scalar. So dii, the diagonal matrix, a diagonal entry in that ith column. Okay. And then, since it's a scalar, I just factor that out and put it in front. And again, P times the I standard vector is just going to be the ith column of P. And what do we have? We have A times P is some scalar times P, or A times Pi is some scalar times Pi. That's a definition of an eigenvector. All right. So Pi is an eigenvector of A with corresponding eigenvalue dii. So that's going to be the diagonal entry corresponding to it. All right. So what have we shown? We've shown that if A has this form, the columns of P are eigenvectors and the corresponding entry in the diagonal matrix is the eigenvalue corresponding to that eigenvector. All right. So let's go the other way. It's an if and only if statement, means I've got double the work, right? If and only if, right there. So let's conversely, assume we have a basis of eigenvectors of Rn. Column P1, P2, Pn. All right, let's throw them into a matrix. Because this is a basis, it means it's linearly independent. So by the invertible matrix theorem, P is invertible. Okay. Also, since pi is an eigenvector, A times pi is lambda I pi for some scaling factor, lambda I. So when we take this, remember what we do is we solve for D in this case. We P inverse out here, P over here. I go ahead and do this. P times EJ is just the jth column of P, right? But we assume that's an eigenvector with eigenvalue lambda, okay, or lambda I. Oh, wait a minute. So this should be I, and that should be I, and that should be I. These should be I's all the way through. I'm sorry about that. And we bring the scalar out front. P inverse of pi is going to be lambda I EI. Okay. All right. And so what do I get? I get that this is going to be the ith column of this matrix here, which is D. All right. So P inverse AP is a diagonal matrix D whose diagonal entries are the eigenvalues of A. All right, so now I can solve for A in terms of the diagonal, and I get A is equal to PD, P inverse is claimed. Done. Okay, all we did was check the answer that was given. Now, of course, there's a lot of it's a long theorem, long stated. Let's see how this might work in some examples. Okay. So let's use some of the work we've already done. So here we had example 1. I'm going to use the exact same matrix I used earlier. And we know what the eigenvalues and eigenvectors are, the basis of the eigenspaces. And so we found that the eigenvalues were lambda 1 equals 0, lambda 2 equals -2, lambda 3 equals 3. Corresponding eigenspaces we're going to have bases corresponding to these vectors. So according to theorem 5, all we need to do is we let P be the matrix whose columns consist of these 3 vectors. And I let D be the diagonal matrix that corresponds to these eigenvalues. Notice that 0 is the eigenvalue corresponding to the first column. -2 is the eigenvalue corresponding to the second column. 3 is the eigenvalue corresponding to the third column. I could rearrange the order of these columns, but if I rearrange the order of these columns, I also have to rearrange the order of these diagonal entries for it to work. So in other words, if I took this vector and put it at the end, that means I'd have to take this eigenvalue and put it down here and move these 2 up, okay? All right, and so P inverse is I can throw that into my calculator and get that P inverse is this matrix. And you can actually check that A is equal to PD, P inverse here, okay? Throw it into your calculators, make sure it works. Let's take a look at example 2, right? We again found a basis of eigenvectors, basis of and eigenvalues. We know what the eigenvalues are. And again, we only had 2 eigenvalues, but we had a basis of 3 eigenvectors. Now, what I can do is, again, I can throw these 3 vectors into the columns of a matrix. But notice that this column corresponds to lambda equals -2, so an eigenvalue of -2. This one also has an eigenvalue of -2. So I had to repeat this in the diagonal matrix, okay? And when I did that, I can still get this whole process to work in that I can find P inverse. Here's P inverse, and I can check that A is equal to PD, P inverse, all right? So that's diagonalization, all right? In example 3, we do the same thing. We did the work on that. Again, we only had 2 eigenvectors. All right, this one corresponding to the eigenvalue of 3, this one corresponding to the eigenvalue of -2. But theorem 5 says since we cannot find a basis of eigenvectors, that B is not diagonalizable. I cannot do this similarity, this conjugation, and get a diagonal matrix. So not all matrices are diagonalizable. We do have this problem when I've got a eigenvalue with multiplicity greater than 1. Okay, note that because of theorem 2, if I have every eigenvalue has multiplicity 1, then I can find this basis and it's diagonalizable. It's always diagonalizable if I have distinct eigenvalues and with multiplicity 1. All right, so I wanted to give you that sense about diagonalization. All right, go through those examples, and we will continue with that on Friday. All right, and we'll see you then. Bye.